Learning with the Illuminati. Part 12. Introduction to the somatosensomotor system. The somatic sensation originates from afferent nerves that have their receptors in the periphery, whereas their cell bodies lie in the central nervous system. These neurons have differences regarding axon diameter, conduction, and myelination, receptor type, and function. The senses, which gives the brain information of location and movements of the body parts, are called the proprioception. The proprioception works by giving continuous and detailed information about the position of the body parts and the mechanical forces within the body. Through receptors located in muscle spindles and in golgi tendons. Receptors in the muscle spindles detects changes in muscle lengths by having group 1 and 2 afferent sensory fibers coiled around intrafusal fibers. When stretched, the tensions opens mechanically gated ion channels, causing action potentials. The signal can travel via dorsal root ganglions to the spinal cord, and thereafter, either back to the muscle, in a so-called reflex, or ascending to the brain. Whereas the receptors in golgi tendon organs detects changes in muscle tension by having group 1b afferents branched along the collagen in the tendons. Group 1a afferent fibers gives rapidly adapting responses, whereas group 2 afferent fibers give slower responses. And the fibers innervating the intrafusal muscle fibers are often called gamma motor neurons. The signals travels to the spinal cord, where the afferent dorsal roots carries sensory information to the central nervous system, and the efferent ventral roots transfer motor information to muscles and glands. The spinal cord can be divided into so-called rexed laminae by the numbers 1 to 10. Proprioceptive afferents from the lower body, synapses with the Clark's nucleus, before continuing via the dorsal spinocerebellar tract, in order to reach the dorsal column nuclei and the cerebellum. Whereas, proprioceptive signals from the upper body, ascends via the dorsal column to the dorsal column nuclei and cerebellum. The target neurons in the dorsal column nuclei, continues across the midline, and through the medial lemniscus, before synapsing with neurons in the ventral posterior nucleus, located in the thalamus. The thalamic neurons send their axons to the somatosensory cortex, which consists of 4 Brodmann areas, of which, the area 3A receive information about proprioception. Control of movement. The neuronal circuits responsible for movements can be classified into 4 subsystems. These are the gray matter in the spinal cord, consisting of lower motor neurons. The cerebral cortex, important for planning and initiation of movements. The cerebellum, which reduces motor errors, causing smoothing of movements. The basal ganglia, important for suppressing unwanted movements. The motor neurons, that innervates a distinct muscle, are grouped into motor pools, and provides a framework for understanding the control of movements and posture. The arms, head and neck, is innervated by cervical and thoracic motor neurons, whereas the legs and the lower back, are innervated by lumbar and sacral motor neurons. In the spinal cord, the neurons are organized in such a way that the proximal motor neurons manages posture, and the proximal muscles, and the distal motor neurons manages the limbs, and distant muscle. The ventral horn has 2 types of motor neurons. The first one are called alpha motor neurons, which innervates the extrafusal muscle fibers, important for posture, movement, and force. Whereas the second group are called gamma motor neurons. These innervate the intrafusal fibers, or muscle spindles, and are important for the regulation of the sensory input. The alpha motor neurons branches within the muscle, in order to innervate multiple muscle fibers, so that the contractile forces can act smoothly across the muscle. One motor unit consists of an alpha motor neuron plus the fibers it innervates. The motor units varies in size and force. Further, the motor units can be either slow, fast fatigue resistant, or fast fatigable. Further, the temporal summation of action potentials can affect the amount of force generated by the muscle. Increased firing rate can lead to an increase in contractile force,